Hi everybody, in this lesson we're going to look at section 5.1, which is our introduction to identities, or look at some fundamental identities, most of which we've already seen in a previous chapter. First, let's remember what an identity is. An identity is an equation that is satisfied by every value in the domain of its variable. In other words, it's an equation that's true for all the different values that that variable can take on. Now, we have seen almost all of the identities in this section before when we went through Chapter 2. You will be given an identity sheet to use on the test, but these identities that we see in this section will not be on the sheet, so you should memorize these, and a lot of them you already have memorized. I think the only thing new that we're going to see here is the negative angle identities. So we'll take a look at those coming up in a minute. And here they are. These are the negative angle identities. We see that the sine of a negative angle is equal to negative sine of the positive angle. And the same thing for cosecant. And we see that cosine of a negative angle is equal to the cosine of the positive angle. And the same thing for secant. And then tangent of a negative angle is equal to the negative tangent of a positive angle. And the same thing for cotangent. So notice that sine and tangent behave the same, and their reciprocals behave the same. It looks like you're just factoring out the negative. You take this negative that's in here and move it to the outside. That's not really what's happening, but that's what it looks like, and that's how you can remember it. On the cosine function, cosine behaves a little differently, so the negative just simply disappears for cosine and for secant. Let's see if we can figure out now why these negative angle identities work the way they do. We'll start with the sine identity. And let's look at a coordinate system that has a positive theta drawn on it, and of course this theta is in quadrant 1. And we could also draw a negative angle the same size that would be in quadrant 4. Now you remember from chapter 2 that these two angles would have to have the same reference angle, and therefore the functions have the same absolute value. In quadrant 1, the sine value will be positive, and in quadrant 4, the sine value will be negative. Well, that's all this is saying, is that the sine of the negative angle is the opposite of the sine of the positive angle. So they're different signs. Now, if we let theta be big enough to go into quadrant 2, then negative theta would be big enough to go into quadrant 3. Sine is positive in quadrant 2, but negative in quadrant 3. And let's also look at the cosine. Same diagram, but we know that cosine is positive in both quadrant 1 and quadrant 4. So here we can say that the cosine of the negative angle is equal to the cosine of the positive angle, because cosine is positive in both quadrants. If we look at a larger theta, then cosine is negative in quadrant 2. It's also negative in quadrant 3. So either way, we get cosine of a negative theta is equal to the cosine of the positive theta. Now the tangent. So same diagram. You'll remember that tangent is positive in quadrant 1 and negative in quadrant 4. And if we look at a larger theta, it's negative in quadrant 2, but positive in quadrant 3. So either way, the tangent of a negative angle is equal to the opposite of the tangent of the same positive angle. Now let's do a few examples together. If tangent of theta equals 2.6, then tangent of negative theta equals negative 2.6. Look back at your identity and remember that the tangent of the positive angle is opposite of the tangent of the negative angle. Okay, number 2, if the cosine of theta equals negative 0.65, then the cosine of negative theta also equals negative 0.65. So for cosine, when we change from positive theta to negative theta, the cosine value stays the same. And on number 5, if sine of theta equals 2/3, then negative sine of negative theta would be negative 2/3, which in other words is positive 2/3. So changing the angle from positive to negative changes the sign of the function, but this changes it back. Now let's take a look at our reciprocal identities, and we are very familiar with these. We've been using these all semester. Cotangent is the reciprocal of tangent, secant is the reciprocal of cosine, and cosecant is the reciprocal of sine. So we can switch between these different reciprocal functions by moving the function from the bottom to the top or the top to the bottom. For example, here cotangent's in the top, but that's equal to having tangent in the bottom. Secant in the top is equal to having cosine in the bottom, and so on. Now let's take a look at a few examples from the end of the section. It says, write in terms of sine and cosine and simplify so that no quotients appear. So that will be our goal through the rest of this section. Simplify so that no quotients appear. Okay, so we'll start by looking at this one. We'll say secant is in the top. That's equivalent to having cosine in the bottom. And with cosecant in the bottom, that's equivalent to having sine in the top. And we haven't looked at quotient identities yet, but you'll see in a few minutes that sine over cosine is equal to tangent, or you may remember that we talked about that in an earlier chapter. And now let's look at this one, cosine times cosecant. Having cosecant in the top is equivalent to having sine in the denominator. So cosine divided by sine reduces to cotangent, and that is another quotient identity that we'll look at in just a minute. Here are our quotient identities, and we've seen these before. For all angles theta for which the denominators are not 0, the following identities hold. Sine divided by cosine equals tangent, and cosine divided by sine equals cotangent. So let's see why these two identities came about. We'll start by looking at a coordinate system that has an angle theta, and we have the radius of the circle here is r, and we know that this point here where the circle meets the terminal side of the angle, this is x comma y, and of course we can draw that little right triangle there and have the horizontal side be x and the vertical side be y. Now, we know from the definition of tangent, that tangent is equal to y over x. And we also know that algebra says we can multiply the top and the bottom by whatever we want to without changing the value of the fraction. So if we multiply by 1 over r over 1 over r, then we'll have y over r for the top and x over r for the bottom. And we remember that y over r is the definition of sine, and x over r is the definition of cosine. So that proves that tangent of theta is equal to sine theta over cosine theta. Also, we know that cotangent is x over y, and for the same reason, we end up with cosine over sine for cotangent. Here are our Pythagorean identities. We've seen these before as well. Sine squared plus cosine squared equals 1. Tangent squared plus 1 equals secant squared. And 1 plus cotangent squared equals cosecant squared. So let's look one at a time and see why these are true. So I'm starting off again with the same coordinate system and an angle theta here. And we'll call that point x comma y. And now, by the Pythagorean theorem, we can say that x squared plus y squared equals r squared. And now we'll go through and divide both sides of our equation by r squared. So we now can take x squared over r squared and write it as x over r squared. and we'll simplify r squared over r squared to 1. Now, when you see it in this form, you may recognize x over r is the definition of cosine. So x over r squared becomes cosine squared, y over r squared becomes sine squared, and that's equal to 1. But usually instead of writing cosine squared plus sine squared, we write sine squared plus cosine squared equals 1. Now to get the other two identities, let's start with this one that we already figured out, and let's go through and divide everything on both sides by sine squared and see what happens. Sine squared divided by sine squared reduces to 1. Cosine over sine reduces to cotangent, so this is cotangent squared, and 1 over sine squared, according to our reciprocal identities, is equal to cosecant squared. So here is the second Pythagorean identity. And let's start with the same basic sine squared plus cosine squared equals 1, and this time we'll divide through by cosine squared. Sine over cosine becomes tangent, so we get tangent squared, and cosine over cosine is 1, and 1 over cosine is secant, so we get tangent squared plus 1 equals secant squared, and there's our third Pythagorean identity. Now, of course, each of these identities has 3 terms, and so they can be arranged into any form we want. For example, if we have sine squared plus cosine squared, instead of having it equal to 1, we could solve the equation for either one of these functions. Let's take a look at it. If we subtract cosine squared from both sides, it will say sine squared equals 1 minus cosine squared. So this is not a different identity, it's just a different form of the same identity. And we want to be on the lookout for expressions that say 1 minus cosine squared, because we can always substitute sine squared in place of 1 minus cosine squared. It makes it a simpler expression to be able to substitute like that. And if you start again with sine squared plus cosine squared equals 1, but this time subtract sine squared from both sides, then it says cosine squared equals 1 minus sine squared. Now if we start with tangent squared plus 1 equals secant squared, we can transform that into secant squared minus tangent squared equals 1, or tangent squared equals secant squared minus 1. And we're just using a little algebra to move the terms from one side of the equal mark to the other. And with the third Pythagorean equation, Pythagorean identity, we can solve for cotangent squared, or we could get both functions on one side of the equal mark and have them equal to 1. So you really don't want to memorize all of these, but you want to be aware that each identity can take on 2 other forms just by moving the terms around. Now, we've seen these problems before. The first example kind of relies on some of the identities, but we're not really going to do all of the algebra identity. We're going to use the function definitions to help us a lot. This one says, if tangent of theta equals negative 5/3 and theta is in quadrant 2, find each function value. Okay, so here's theta in quadrant 2, and remember the definition of tangent is y over x. So 5 is y and 3 is x, and we'll use the Pythagorean theorem to find the missing hypotenuse. We'll add the squares, so 25 plus 9 is 34, and that means that r is the square root of 34. Okay, now secant, we know, is r over x. Remember, cosine is x over r, secant is r over x. And because we're in the second quadrant, cosines and secants should be negative. So this is negative square root of 34 over 3. Sine is going to be 5 over square root of 34. But we have to rationalize, so that will become 5 square root of 34 over 34. And cotangent, well, we know from our negative angle identity that cotangent of negative theta is equal to negative cotangent of positive theta. Now we needed to do that because our diagram is not going to tell us the cotangent of negative theta, it's going to give us cotangent of positive theta. So tangent is y over x, cotangent is x over y. So this will be negative 3/5, because remember, in quadrant 2, cotangents are negative. This negative is this one that you see here. The cotangent of theta is negative 3/5, so negative 3/5 is equal to positive 3/5. Now let's look at number 13 from page 194. Similar type of problem, but they did not tell us what quadrant theta is in. This time they said if tangent of theta is negative square root of 6 over 2 and cosine of theta is positive, find sine of theta. Well, we know that if tangent is negative and cosine is positive, our angle has to be in quadrant 4. So now if we label the sides using the definition of tangent, this is y over x, so our two sides are square root of 6 and 2. And we'll use the Pythagorean theorem to find the missing hypotenuse. So we'll do 2 squared is 4, square root of 6 squared is 6, 4 plus 6 is 10. That missing side is square root of 10. Okay, now sine of theta is going to be y over r, but it's negative because we're in the fourth quadrant. So negative square root of 6 over square root of 10. Let's rationalize. That will give us negative 60 over negative square root of 60 over 10. And then, of course, 60 is 4 times 15. So the square root of 4 is 2. And that means that 2 will come out of the radical. And now 2 over 10 reduces to 1 over 5, so we end up with negative square root of 15 over 5. And here's another similar problem. If secant of theta is 4/3 and sine of theta is negative, find the remaining 5 trig functions. Well, we just have to remember that secant is the reciprocal of cosine, so cosine is 3 over 4. That means we've got here x over r, so x is 3, r is 4, and we need to label this missing side, so we'll subtract these squares. 4 squared minus 3 squared is 16 minus 9, which is 7, and that means y squared is 7, so y is square root of 7. Alright, now it's going to be easy to get our 5 functions. Sine is y over r, and it's in the fourth quadrant, so it should be negative y over r. Cosine is pretty much given to us, it's just the reciprocal of 4/3. And tangent is y over x, and it needs to be negative, so negative square root of 7 over 3. Then the next 3 functions we can get by doing reciprocals of the first 3. So the reciprocal of sine is cosecant, so that will be negative 4 over square root of 7, but we should rationalize that and get negative 4 square root of 7 over 7. Secant was given to us in the problem, and cotangent is the reciprocal of tangent, so it's going to be negative 3 square root of 7 over 7. Okay, now we come to what this section and this entire chapter really is about, which is taking a complicated expression and simplifying it to something less complicated. So what they suggest we do here is write each expression in terms of sine and cosine and use that to simplify so that no quotients appear in the final expression. All functions are of theta only. So what they mean by that is no fair leaving the answer like a tangent of negative theta. It has to be a function of theta. So let's start by changing tangent to a sine over cosine form. That's a quotient identity that lets us do that. And then, so tangent times cosine becomes sine over cosine times cosine. Of course, the cosines will simplify, and we're left with sine of theta. For the next one, we'll use a reciprocal identity to change cosecant into 1 over sine. Cosine can stay the way it is, and tangent is sine over cosine. Now, your cosines will simplify, and your sines will simplify, and that leaves simply 1. Here's another example. Same instructions. Write each expression in terms of sine and cosine and simplify so that no quotients appear in the final expression. Well, this looks like a FOIL method problem, and it's a binomial multiplication. So in fact, we should use the FOIL method. I have gone ahead here and changed cosecant into 1 over sine and secant into 1 over cosine. You don't have to. You can do that later if you want to. It has to be done at some point. I just went ahead and did it now. So now let's use the FOIL method. Sine times 1 over sine will be sine over sine. Outer times outer will be sine over cosine. Inner times inner will be minus cosine over sine. And last times last will be minus cosine over cosine. So simplifying now, sine over sine becomes 1. Sine over cosine becomes tangent. Cosine over sine becomes cotangent. And cosine over cosine becomes 1. Now notice that 1 minus 1 will add up to 0. So we are left with simply tangent of theta minus cotangent of theta. Another example, similar instructions. Write each expression in terms of sine and cosine and simplify so that no quotients appear. So I notice first that we have secant squared minus 1, which makes me think of one of our Pythagorean identities. You remember that we had 1 plus tangent squared equals secant squared. So if I could rearrange my terms so that one side says secant squared minus 1, I could make a substitution. And by moving the 1 to the right side, I get tangent squared equals secant squared minus 1. And the same thing for the bottom. If we take 1 plus cotangent squared equals cosecant squared, but we subtract 1 from both sides, we get cotangent squared equals cosecant squared minus 1. Then we can say secant squared minus 1 is equal to tangent squared, and cosecant squared minus 1 is equal to cotangent squared. And now, using a reciprocal identity, we can say that cotangent in the bottom is equal to having tangent in the top. So tangent squared divided by cotangent squared becomes tangent squared times tangent squared, which is tangent to the 4th. Let's now write 1 plus cotangent squared over 1 minus cosecant squared in terms of sine and cosine, and we'll simplify it the same way that we did before. No quotients left in our answer. So I've got 1 plus cotangent squared over 1 minus cosecant squared. This time I'm going to do a little differently. I'm going to write cotangent as cosine over sine. There's no reason why you couldn't go ahead and make a Pythagorean substitution there if you wanted to. I just want to show you a different approach. Now we've got common denominator here of sine squared. So let's multiply the top and the bottom by sine squared and see what happens. Sine squared times 1 is sine squared. Sine squared times this fraction will be cosine squared, because notice your sine squareds will cancel. And in the bottom, sine squared times 1, and then sine squared times this fraction. Now we can simplify, like I said, the sine squareds here, and also there in the bottom, and we end up with sine squared theta plus cosine squared theta over sine squared theta minus 1. And notice that sine squared plus cosine squared is one of our Pythagorean identities, so that equals 1 over sine squared theta minus 1. Now, if you think about our Pythagorean identity here, I'm trying to make a substitution here. Sine squared theta minus 1, if I could look at my Pythagorean identity that contains sine squared and figure out a way to make it say sine squared minus 1. See, if I just subtract 1 from both sides and then subtract cosine from both sides, I see that sine squared theta minus 1 equals negative cosine squared theta So I can replace sine squared theta minus 1 with negative cosine squared theta. And then, in order to not leave it as a fraction, we'll use a reciprocal identity so that cosine in the bottom is equivalent to having secant in the top. It's negative, so it stays negative. And we have simplified this complicated expression down to just negative secant squared. Now, just a little word of caution. I see a lot of people being really careless with their writing. When you write an identity, you cannot leave off the angle. We tend to do that when we're talking, but you really don't need to do it when you're writing. It doesn't mean anything to write sine squared plus cosine squared equals 1. You need an argument. You need an angle there. So it needs to say sine squared theta plus cosine squared theta equals 1. It's very important to have the angle there, because later on we're going to have identities that contain more than one angle, and so you'll really need to specify which one you're talking about. But even if you're not, it's just good practice to put that angle there. Otherwise, somebody who's reading this doesn't know what angle you're trying to refer to. Okay, we've just got a couple more examples here in section 5.1. Let's do the same thing again. Write each expression in terms of sine and cosine and simplify. So we'll start off by changing cosecant to 1 over sine. And now we're going to use common denominators to combine these two fractions into one. This one has a denominator of sine. If this one has a denominator of sine, I'll have to put a sine in the top. So we've multiplied by sine over sine, which is like multiplying by a big fancy 1. And that gives us for the top 1 minus sine squared, and for the bottom simply sine. Now 1 minus sine squared, if you remember, is very similar to one of our Pythagorean identities. So if we start with sine squared plus cosine squared equals 1, and we rearrange it so that it says 1 minus sine squared, we can see that that's equal to cosine squared. So we get to replace our numerator with cosine squared, and the denominator is still sine. Now, if I separate this cosine squared into two cosine factors, I can see that cosine over sine will become cotangent, and we're now left with cotangent times cosine. And number 69, 1 plus tangent of negative theta all over tangent of negative theta. First, let's split this into two separate fractions, and so now we say 1 over tangent of negative theta is equal to cotangent of negative theta, and of course tangent of negative theta over tangent of negative theta would become 1, because anything divided by itself is 1. Now we know from our negative angle identities that cotangent of negative theta is equal to the negative cotangent of positive theta, and then we have this plus 1. Now I want you to pay close attention to how we separated these into two fractions here. If you have more than one term in the top, you can split it into two fractions by giving each term its own copy of the denominator. And that's always a legal move. It has to be from the top, though. You can only split fractions if you have multiple terms in the top, and then each fraction gets the entire denominator.